Hello, hello. Sorry. I love it. I love it. Hello, Stephanie. Good afternoon, iPhone. Good afternoon, Andrew. Oh, I see you. Oh, good afternoon. Double good afternoon, Andrew. Good afternoon, we she. Wait, that might be a double. Yes, good double good afternoon, we she. Good afternoon, Vivian. Good afternoon, Lakshmi. Good afternoon, Jaylyn. Good afternoon, Mark, and everyone on behalf of Mark. Hi, Michaela. Double good afternoon to Gabriella. Like that's a double because of video, right? You get it. Okay. Good. And good afternoon to everyone on behalf of Gabriella. That's awesome. Okay. Good afternoon, you people. It's a little okay. I don't know. I think you can change that. Good afternoon, Alyssa. I didn't even know what IDK stood for until I did. Okay, wait, more people are coming. I think you can, well, I can change that if you can. Okay, hold on. I might change, don't, I might be able to change that. Okay, more people are coming. Well, who else? Oh, sorry, okay. Oh, I spelled Alyssa wrong. Whoops, sorry. Ignore, do not, I didn't do that. That was a person who, okay, and okay, just to get revenge. Okay, thank you. Okay. No. Oh, and so they're eating carbohydrates. Okay. Oh, that was a private message. Sorry. Well, I'm not going to say who told me that, but I don't even get. Okay. Thank you. I'm sure they appreciate that you've got their back. Private message, secret person. Okay, that is hilarious. Okay. Oh, and also good afternoon, Brenda. Good afternoon, Josephine, whose name I'm still not pronouncing right. And that is, and Michaela, if I didn't say, and Stephanie, if I didn't say. Oh, but you guys are here. And Celine. Okay. Good afternoon. All right. Oh, and more people are still coming. Oh, this is like I know I dragged this part out, but it's kind of my favorite part of the class. And it's definitely the most challenging part of the class. All these names will be on your exam, by the way. Okay. Yes. Good afternoon, Brenda. Yeah, well, I figured my name had to be misspelled for a little while. Thank you for noticing, because I mean, if Alyssa's name is going to be misspelled in public, it's the least. All right, but it's probably going to confuse people. Yeah, I have a feeling that's the way it was originally spelled back when, Baum, you might all know. So good afternoon, Josephine. Yes. And by the way, and that's not a private jet. When you say Yavram evolved into a Yaverbaum, but then I just de-evolved back or devolved. I don't know if you mean that like in the biological sense of evolved or the Pokemon sense of evolved, which of course in Pokemon, the way they use the word evolved, really they mean metamorphosize if you think about it. Like they're not actually using the word correctly, but I love how in Pokemon, for anybody who knows what I'm talking about, I love how people will say they'll say they'll say Raichu is the, now of course, if you don't know what I'm talking about, this is like completely a waste of like stupid, but if you do know, like they'll say like Raichu is the evolution or evolution of Pikachu. But then if they want to say that in reverse, if they want to say that Pikachu evolves into Raichu, they say that Pikachu is the de-evolution of Raichu, which is like such a strange thing to say. Like that is, I can't explain why I think that's so weird, but it's like, I mean, it's like saying, I guess it's like saying ape is the ancestor of humans, but instead of saying ape is the ancestor, or like instead of saying primates are the ancestors of humans, saying that primates are the de-evolution of humans, as though if like the second law of thermodynamics were to like be flipped, we would start like running time in reverse and like we would degenerate back into, I don't know, that's just such a weird image. But okay, more people are coming. Sorry. All of the stalling is just to let everybody have a chance to come to class. What? Oh, okay. Oh, you did mean in a Pokemon way. That's hilarious. Okay. Oh my God. Okay. You guys are way ahead. See, I can't even make, I try to like, I can't even make jokes that are ahead of this class. Like even your jokes are ahead of me. Good afternoon, private chat person. Okay, and people are still coming. All of my stalling is just to let people come in without embarrassing them. I promise it's all part of the curriculum. It's all in the exam. Now we're going to start in a second, but thank you all. People are coming in. Thank you for the Pokemon participation. I think Pokemon is brilliant, brilliant. Literally, oh, okay, no problem, no problem. Thank you, direct chat person. I understand. Hello, Jayla. Okay, we honestly, I mean, good afternoon, Jayla. We will really start in a second. But yeah, I think Pokemon's great. And honestly, I spent a lot of my life doing math and physics, obviously, like I might have mentioned in this class. I mean, I've been teaching physics since 1992, which is weird even to me to say that. Like, I know that's like before some of you were born. I've been teaching physics and other related subjects since 1992. But the one thing I like never understood for you, so I'm always in a science department. Like I'm everywhere I've worked, of course, I'm in some kind of science department. So I'm always like working as a scientist. But for years and years and years, I did not feel like a scientist at all. I mean, I'm not even just talking about imposter syndrome or whatever, which I think everybody has, but except for people who fake imposter syndrome because they're such imposters. But like for the longest time, I didn't identify as a scientist. I just thought I was more like a glorified math guy or like a glorified theology guy or something, because I so did not get biology. Like I didn't feel connected to biology at all. I'm not saying I didn't like it. And I'm not even saying I did badly at it, like in high school, but like I just didn't get it. I just didn't get it. Probably, honestly, because biology is like all about life. And to me, life is just like one hair's breadth away from death, and death scares me. So I just rather deal with math and physics where everything's dead all the time, so it never dies. But anyway, there's two things that got me to actually start appreciating biology. Honestly, one of them is Professor Walters, who some of you have had. Like he literally one night opened my eyes to the beauty of biology, like single-handedly showed me what makes him love biology, and it made me love it. And the other thing that made me open my eyes to at least what the attraction of biology is Pokemon. Like for real, like I could discuss that another time, but I'm not saying I'm not saying Pokemon is like biologically like valid, but just like the whole like world of all these different creatures that are all alive, and there's just like always more of them, and you could sort of organize them in a taxonomy, but you sort of can't. And it's just like there's rules, but they're sort of like loose, but it's not like math. It's like Pokemon. And I started to get like, oh, maybe this is what, and it's like so colorful. And I was like, oh, maybe this is what people like about like studying life. Oh, I get it, sort of, but that's probably not what they like. Anyway, all right, let's do physics. Sorry about the delay. And hello, Celine. Hello, Celine. Celine. Hello, not salt. Celine. Okay. Hello. Okay. We're going to go back to thing on a spring. I'm also going to quickly say the logistical yeah. Okay. We're going to go back to the thing on a spring. Thank you. Thank you, Mark. Oh, okay. I could quit now. I'll take it. Thank you. He's like, if you didn't stutter so much and didn't say 4 times, it might have almost been like normal. Okay. We're going to go back to the thing on a spring. We're going to continue going over homework 1. There's a lot going on in homework 1. Again, you're not going to get a new assignment for a little while. Also, I still need to get you back. Many of you homework 1s. I apologize. I'm still a little bit like spazzy at this point in the year. I also owe you some game turns. You owe me one as of tonight, but I'm aware of all that. They will come back. You're not going to get new homework for a while. We're going to just keep working on homework 1 because there's a lot going on there, a lot of like subtopics that we're opening up, and I will get to those subtopics in a moment. Let me just also say, I will say, right. So homework 1 is what we're about to talk about, which specifically means, and question number, I believe it was question number 4, which gets us into energy, right? We just gotten off the ground with that time. We have to get into work, kinetic energy, and potential energy today. More people coming, but there's one logistical thing which I want to slow down to say tomorrow, and maybe I should put this in. A lot of people coming. Oh, people having internet connection problem. Okay, people are falling in and out. Let me say one thing as clearly as possible and slowly as possible. Tomorrow, you have lab. I mean, correct me if I'm wrong, but I believe that this section has lab tomorrow at 3:05, stop me in the chat if I'm wrong so far, but I believe that you have lab tomorrow at 3:05. You've been online well, you were online last week. As of this week, you are back into reality, into the lab room. That's right. Okay, thank you, Stephanie. In fact, okay, great. This is actually just serious enough. We do, thank you, all of you. Thank you, Jayla. Thank you, Alyssa. Thank you, Stephanie. So I'm going to put in the chat right now, and I'll try to remember to put this in Google Classroom, but tomorrow lab is back in reality in the lab room, which I'm writing in the chat if you've never been there. Maybe you've never been there before. Hold on, sorry. Okay, it's in the physics lab. Now that I'm thinking of it, some of you may never have been in the physics lab before. It's in the physics lab starting tomorrow. That's 03.65. I'm pretty sure it says on your schedule. So it's on the 3rd floor. Okay. Well, to be as blunt as possible. So physically, please go there for lab tomorrow. I got some questions over the weekend whether your report was due tomorrow or not. Of course, there's legitimate confusion about that because it's been a funny schedule. Whoever asked me, I said, no, don't worry about a formal report or anything due tomorrow. If you did it, great. But as far as your instructor, tomorrow it will be me. Okay. I will look forward to seeing you and meeting you in real person and getting us off the ground with lab tomorrow. It will not be me permanently. I have a teaching conflict at that time. To be totally honest, we're still working out an instructor. Like your Professor Wu was caught in China and we can't get him back. And that's a crushing thing to me. It's just the reality right now. So tomorrow it's me. TBA what's happening after that. But it is back physically. So, oh snap. I don't know what snap is. Oh, snap. Oh my God. Pokemon Snap? Okay, so yeah, so I will see you tomorrow at 3:05. And again, correct me if I'm wrong about, but I believe, it's supposed to be Wu and it's supposed to be in the laboratory, blah, 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 so it's not Wu, it's me. After that, we're going to see. But anyway, so please, let me know in private if you're having an issue or if there's confusion. But don't worry about having done anything for tomorrow. Just I'll see you there. Okay, and I'm going to one other thing. I'm turning off notifications. So then we're going to now start. Oh, that's hilarious. Yeah, please do. Oh my God, totally. Please do that. Yes, I mean, we'll probably get more done that way. I would have never guessed that you had a Nintendo Switch cabriolet. It's not clear at all. Just kidding. Okay, no, that's awesome. I'm a total believer. If I haven't mentioned. Okay, I'm making up for lost time with video games. Obviously, I'm at this point a big fan, and that's also thanks to Professor Walters in a big way. But okay, and my sons. But okay, so we're gonna now back to physics. Oh yeah, right. So those of you who have this is all old news. So much of this is all old news to you. But I'm looking at you. Oh yeah. Oh, okay. Direct chat. Yeah, totally. I love. Again, I know this could be alienating because some of you are not, it's not, video games are not a prerequisite for physics classes, even though they're beginning to seem that way. If you don't like video games, I totally respect that and no problem. And it's not, and I felt that way for a long time too. So I really do get it. But if you do know what Animal Crossing is, yes, our participation homework is totally based on Nook miles for what it's okay. We got to do physics now. I'm sorry, I'm getting it. Last legit. Okay, so we're gonna go to thing on a spring. Because I want to get back to the curriculum here. I also want to say one other thing. There's 2 online sections of physics. There's this section, section 1, and there's also section 2. That meets at 3:05 p.m. And I post I post the recordings from both classes on YouTube. We're of course in step. We're doing the same material, both sections, but of course I do it slightly. I emphasize slightly different things in each section each day. So this is one time I want to encourage you right now. I got to a certain point already with the other section on this topic. And then today I'm going to abbreviate it slightly with them and have to do something else. I want to let you know right now that, especially in this topic right now, if you're really trying to stay on top of the material, or if this material is new to you at all or fuzzy, like work energy integrals, that's what we're about to get into right now. If it's at all new or at all fuzzy or anything, I actually recommend that you watch the videos from both classes, honestly, or at least pay attention to this class and then watch the videos from the other section, because I'm actually at this point consciously and explicitly doing it two slightly different ways in the two classes so that together you can have as much perspective as possible. Because that's serious advice. Like, of course, if it's clear, then don't worry. But if you want more, the other section, I'm doing it differently on purpose. So one perspective might work for one of you better than the other. Okay, so just check out the other section videos. Like, these are called technically noon and those are called afternoon, whatever. Okay, so all that said, but again, so I'm going back to homework 1 here. I'm going back to homework 1, and I'm going to question, I believe it's question 4. You stop me also if I believe where we left off last time, I believe is question 4. And I believe okay, this is, again, please, now I'm like trying to, please stop me if I'm off base or if I'm starting at the wrong point or if anything I'm saying is unclear, but this is where I think we are now. Back to the serious material. We're on a thing in the spring sheet, like the diagram you have from above, blah, 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 but we should be looking at the diagram and knowing the facts while I'm considering all this. We're question, what I believe is 4, where I think the question is, at equilibrium, when the mass arrives at the equilibrium position, what is its instantaneous, oh, did I even have, yeah, what is its instantaneous speed? Technically is what the question's asked, or, what's the magnitude of the velocity? And we decided last time that this sounds like a kinematics question. It sounds like a question where we would relate, like where we would use acceleration and or force to determine velocity. But we realized that since the force, and therefore the acceleration, is varying continuously as a function of position, because it's varying continuously as a function of position, then we decided, first of all, kinematics are out. Constant acceleration equations are out. They're true, but they're not helpful because literally the acceleration is not a constant, it is varying. But then we went a step further and we said, okay, what do we do in physics? What do we do when we can't use constant acceleration because the acceleration is not a constant? Like, what model, what approach, what equations do we choose? Well, this is always like a trick in physics. If what's the problem? The problem is the force is changing. And I say changing continuously. Please remember when I say or varying continuously, that's not just like that's not just like a strong English statement. When I say that it's varying continuously, I don't just mean it's varying like a lot, like often, like it's just no matter what we do, it just keeps on varying. Like that is partly what I mean. But specifically when I say continuously, I don't just mean continually. I mean continuously. I mean that for every new position, there's a new force. And when I say every position, I mean every new infinitesimal position. I mean, it's not just like, it doesn't just go in stages, like when the position is 1 meter, the force is this, all the way until 2 meters. And then when it is 2 meters, the force is this. And then all the way the same until 3 meters. Like that would be one thing. That would be like a stepwise thing. That would be an issue, but we would just then divide the problem into a bunch of steps and just solve the problem for each step. If that were true, we're saying that the force varies continuously, like throughout, smoothly through every conceivable value of position that you can conceive. And we're saying it varies as a continuous function of position as opposed to time. Okay, as opposed to time. We're saying every new position, there's a new force. So on the one hand, that is the problem. That is why we can't use old methods to solve. But since we've really specifically defined our problem is not just, oh, the force isn't constant. Our problem is the force is varying continuously as a function of position. Then what we do is, oh, let's construct for all time, not just for this one case. Let's look at what we get when we multiply force by position for a continuous stream of positions. Like, in other words, what I'm saying down here in the right-hand corner, okay, like I started, I think, saying this last time, but I'm not even sure. Well, I'm saying I'm writing a big W, which stands for work. I'm saying we're going to toss out kinematics and free body diagrams and all that. We're going to start thinking about work and energy. I'm saying specifically that the time to use work and energy is when force varies continuously as a function of position, because work is defined to be just that. Work is mathematically work, W, so W stands for work over here, okay? W, triple equal sign, work is the continuous sum. That, I know that's an integral, right? It's an integral, but what is an integral? An integral is a smooth long S, which stands for sum. What an integral is a sum of force, in this case, force times change in positions, displacements. Work is the sum of force times displacements. It's the ultimate result or consequence or accumulation or impact or outcome of what happens when you push or pull something through a displacement. Work is force times displacement added up for a whole bunch of force times displacements. Work is the continuous sum of force displacement products. It is the integral of force with respect to displacement. But what really is an integral? I know we've all been required to take calculus and all that, but come on, let's be like, that doesn't mean we get it. It means we got through it. I certainly did a lot of integrals without ever feeling comfortable knowing what the heck they were or how to set them up or why or when. What an integral is a big S. It is a sum, a continuous sum of products. What kind of product? Always a dependent variable times an independent variable. It's always a product of something that's going on times the varying value on which it depends. Always. An integral is always something times a d. And in this case, it is the continuous sum of forces through little displacements. When I say continuous sum, I mean it's just a sum. It's a sum of force times displacements, but taken to the limit as each displacement approaches zero, meaning it's the kind of sum we do when we don't have the advantage of being like, for the first meter, the force is this. Then discretely and rigidly and very visibly, it changes. In the next meter, the force is this. And in the next, in other words, what I'm saying is this. What I'm saying is this. Suddenly this is looking like math, right? But really, please look at what and suddenly maybe it's looking like calculus. To me, what I'm doing now is not demanding that you remember all the calculus that you were forced to take for this. What I'm really doing now is trying to say, like, let's take a step back and look at the calculus that we've been doing in our other lives, and let's look at what it really is meant to mean. Because frankly, at least to me, I didn't get calculus at all until I saw how it was panning out through physics. Okay, what I'm saying here mathematically is that an integral, a smooth S integral, is really a sum, a discrete sum, like what an integral is. If you look on the right-hand side, it's the sum of what happens when you multiply force times displacement and add like force times displacement through here plus force times displacement through. What if I have a really long displacement to go through? If I first walk a little section of the displacement, the first little displacement, ask what the force is being applied there, multiply the two together, throw it in my bag. Then I go to the next little displacement, so like the next meter, ask what the force is being applied there, multiply the two together, throw it in the bag. Then I go to the next one, multiply the two, throw it in the bag. If I were to do all that, that's called the sum of products. And if I did it for all the little displacements I had and just add them all, then I would have the total amount of what we're defining to be work, the total effect, the total accumulated result of what it means to push or pull something through space. It's kind of like the total result of your efforts. That's what's on the right side. But then I'm just saying, and right, so I'm really saying that what I'm saying here, and again, I'm sort of saying, if you watch the other video, like I explained this whole thing, but sort of like in the opposite order. I'm saying here, work, we just define to be force through a displacement, force multiplied by a displacement. We define it. It's like, if you don't have any displacement, if you don't put any, so work is interaction and result. How much you're interacting with another object and how much that interaction is resulting in changing the state of that other object. In this case, changing its position, displacing it through space. So if you don't push something at all, you're not doing any work. If you push something, but you don't succeed at all, it doesn't get anywhere, it doesn't move anywhere, then you didn't do any work. The more you push or pull, and the more something is moved, the more work you've done. So work, we're just defining to be a push or a pull times a displacement. Again, secretly, we're defining it that way, not just like randomly. We're defining the concept of force acting through an interval of space because we ultimately want to be able to deal with situations where we have forces that vary through space. Up until now, everything in physics has been like derivatives. Everything has been like, if you know all the forces acting on one point in space and time, then you can infer the acceleration, the instantaneous acceleration at one point in space and time. Like everything now, up until now, is free body diagram at a point in space and time, get the A of the object at a point in space and time, and then infer from that what the instantaneous velocity of the object will be at some later point in space and time. Now we're saying, like, can't we just like navigate through space and time? Can we know what's going on when things are being pushed or pulled from one point to another? So we define and we say, from now on, there's this construct called work, where you push or pull something from one point, like through points in space and time. We're going to say that a little bit of work, delta W, is defined, triple equal sign, to be force times a little bit of displacement, delta X. When I use delta in math or physics, you might want to write this down. When I use delta, some of you who think of delta as meaning change, I would say delta really means difference. In fact, please do write this down. In math or physics, delta means delta. Please write this down if you're paying attention. I mean, I would, but I'm going to like mess up the flow that I don't have. Delta means small but finite difference between two values of a variable. Delta means small but finite difference between two values of a variable, as in delta y equals y2 minus y1. We call that rise. Delta x means x2 minus x1. We call that run. Delta y over delta x is slope, right? Deltas are differences, finite, measurable, observable differences between values of variables. So a little delta, a little difference between two values of x, a little finite but small displacement with a force acting through it. So if I push a box through a small displacement, we're going to call that a little bit of work. And we're also going to notice like that unit wise, 1 Newton of force times 1 meter of displacement. We're going to, from here on in, call 1 unit of work. And that unit of work is called a joule. Okay, again, like all these are pieces that you've probably seen. I'm just trying to put them together in a certain way. So a little bit of work, a small but finite amount of work, is defined to be a force acting through a small but finite displacement. A little bit of displacement. And then you reasonably, of course, oh, how little? Wait, what do you mean small displacement? What do you mean small amount of work? How small are you talking about? Yeah, how little is little? And I say little enough. This definition that work is force times displacement totally like applies and is usable as long as the displacement is small enough that the force doesn't have very much room to vary. For any amount of displacement that's small enough that there is one F that I can even picture or measure or imagine applying to that delta X, then I take the F, the number of newtons. So it's like I push a box with 5 newtons of force through a displacement of 3 meters. As long as the 3 is small enough, as long as 3 meters is a small enough space that the 5 doesn't really have room to vary, that I just keep pushing a 5. Then I say work is 5 newtons times 3 meters of displacement, and that's called 15 joules of work. That would be the end of it. And then I'm going to do stuff with that. But like it's a way of like talking about how force will achieve something from one position to another. That would be the end of the work definition. But then if I want to back up and say, okay, hold on, the whole purpose of this, the whole purpose of defining something as the force times the displacement, the whole purpose is to ultimately look at displacements that are large enough to account for changing forces. That's the purpose, and that's why we're looking at it in the context of a spring. Then what do we do then? What do we do if the displacement is large enough to allow forces to vary? So I say, well, the whole is equal to the sum of its parts. If we all are going to believe and trust that a little bit of work is a little bit of force times a little bit of displacement, then if you want to know the work over a large displacement, just divide the displacement, the large displacement, into a lot of little chunks, each of which is small enough to allow for one little constant value of force. So if you want to know, so this is what I'm talking about right now. I know I'm kind of all over the place, kind of, but not really. What I'm saying right now is, I mean, it's certainly yelling, that's for sure, but what I'm talking about right now is this side. I'm saying, and this side really means in English, the whole is equal to the sum of its parts. That if we have a definition of what it would mean for work over a small interval would be, then work over a big interval would just be the sum of all the little constituent works over the little constituent small intervals. So you divide a 15-meter displacement into like the first meter where the force is 2 newtons, and you multiply them together. Okay, 1 meter times 2 newtons, that's 2 joules of work you put in your bag. Then you go to the next meter, you say, in this next 1 meter, the force is now 3 newtons apparently. So I multiply 3. Yeah, right. Okay, awesome. I just got something in the direct chat that's awesome. And I'm going to say, yeah, the answer is yes. And I'm going to expand on that in a moment, but great question in direct chat. And yes, woohoo, yeah, totally. And you should have gone public with that because you you totally get points for that. I'm going to put a portal in and blah, blah. But yes, let me address that direct chat person to everybody in once. I'm just going to finish my thought before I die. And then I'm going to say that thought. But yeah, so what I'm saying now to everybody is, if we believe that the whole is equal to the sum of its parts, if we want to know the displacement, if we want to know the work for really big and by the way, that also really shows that you're paying attention. So thank you. That's at least one person who's clearly, totally, deeply, not only paying attention to me, but paying. Anyway, what I'm saying is, look. Okay, cool. First meter, it's 2 newtons of force, so I multiply them. I get 2 newtons of force times 1 meter. Okay, that's 2 joules I put in my bag. Then I go to the next meter and I say, okay, this 1 meter again, but this time it's 3 newtons of force, so I do 3 times 1. That's 3 joules put in my bag. I have a total of 5 now. Then I go to the next. Oh, now the force is 4 newtons. Multiply that by 1 meter and I put it in my bag. I think we can all agree that if I added all those up, I would get the total work for the whole thing. I would. And that's the only, so that's all I would ever need to do in life is just take the sum of all the little works. But we're here to acknowledge the very real possibility that force might vary continuously, or that any dependent variable, any quantity might vary as a continuous function of the independent variable. That, as in the case with the spring, the force exerted by the spring doesn't change in chunks. It changes smoothly. Every new little millimeter you pick has a new value of force. So we want to add up all these products, but in the limit as the second multiplicand, the second number in the product, actually goes to 0. So if we were picturing this on a graph, we're like saying we want to add up a whole bunch of rectangles. Why rectangle? Because we've length, force on a graph. Like we'd be graphing force as a function of position. So we'd be adding up all these force position products, all these height, width products, but we'd want to go to the limit as the width approached 0 if we really wanted an exact result. Now what someone, and that limit, the limit of the sum is the continuous sum, which we call an integral. Now I'm going to slow down for a second. First of all, and again, to all of you, in a way, this is old news. I know that. And it's also like math, not physics in a way. But what I'm also secretly hoping or believing, if my past experience means anything, is that to many of you, you may have heard this a million times, but maybe, hopefully, this is a little bit worth it, because maybe for some of you, it's starting to click into place really what an integral actually is and why we ever care about it in the first place. No. Like, so someone in the direct chat just very, very correctly and like yay-ishly said, am I talking about Riemann sums? Oh, yes. Everything I've just said is like the physics version of a Riemann sum. Or put another way, Riemann sum is the general idea of those rectangles under any general graph where you have anything on the y-axis and anything on the x-axis. Here I'm saying our particular example of the first time we would ever want where we would want to add up a bunch of rectangles and then make the rectangles smaller and smaller and smaller in width until there was no missing pieces at all to the area that we were calculating. In physical terms, the example of this is, what if our dependent variable were position and our independent variable were force? That's the first physical example where this would ever happen. And the reason you would be interested in the area under the force position curve is because area just means multiply like length times width or height times width. And our physical construct says we want to know the product of force with displacement. And we're assuming force is some kind of function of displacement. So yeah, we're saying what we want is the Riemann sum. Yes. We want the limit, we want the sum of all these products taken to the limit, i.e. we want the continuous sum of all these products. So this absolutely is like that Riemann. Yes, if you've ever heard of Riemann sums or felt you wow, my pen just went flying. Or like, yes, this is the classic central primary most vivid physics illustration. Like the first real integral in physics is the force displacement integral, which we call work. It's the first time we would want an integral. Yes, technically you're required to already know integrals before you come into a physics class and do this. But honestly, if you're like me, you didn't understand integrals until you saw, for me, I began to understand integrals once I thought of them like the general idea behind work. Like I needed the physics example to make it make sense to me. So hopefully this is helping maybe some of you now. So I'm saying now, the integral is defined to be the continuous sum. Yes, it's the continuous sum of, it's the Riemann sum idea. That's awesome that someone said that. Totally yes. And I'm saying, so an integral in general is a continuous sum. That is all it is. An integral is always a continuous sum of products. It's always a sum of products. And the product is always the dependent variable times the independent variable. Okay. And I'm saying in physics terms, just go back for a second. Yeah. This particular integral of force, specifically times displacement, is called the work integral. It's called work. Okay. And I'm saying at this moment, whether it's the first time you've heard this or the millionth time you've heard this, right now, all I'm doing is defining something. I'm saying that work from here on in is the integral. So I'm saying yeah, all I'm saying right now is that work is defined to be the continuous sum, the integral of force with respect to displacement. Hopefully this discussion, if anything, makes a little bit more vivid what an integral is or what an integral means or why we would ever care about one. The answer is because it's a continuous sum. You'll know that you really are following what I'm saying. Okay, and of course now I have to go a step further. Notice that nothing in what I'm saying tells you how to solve an integral, nor what to do. It does. Well, I'll write this down. I just want to be as clear as I'm looking in the chat. Yeah, okay. I just want to, no, and again, yes, the person who said Riemann sum, and any of you who might have been thinking anything like that or even paying attention to me at all, like, yay. If you're feeling any connection at all, if you're seeing any calculus like come a little bit into focus for you in a physics way, yay. And if you're spending even 1 millisecond saying to yourself like, oh, is this what I was supposed to have understood last year? Or, oh, I didn't get, don't make that face that I just made. like, this is not the time to be like, oh, I was supposed to get this before, I never quite did. Nor is this the time to go, I never liked this crap before, I'm gonna like tune out now. No, 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 no. Like, I didn't either. If you can get it now, then you rock, and don't worry about whether you got it before or not. Blah 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 blah. And if you didn't get it before, don't tune out now. Tune in now. Blah 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 blah. Like, the secret underbelly of Physics 204 is partly we're trying to. It's like our last ditch effort to actually learn and teach calculus. It's not an assumption that you get it. It's here. Let's get it. Okay. Anyway, now in effort to. So if you're making any connections at all, Quark bless America. But here's a way to know whether you're with me or not. Please know, for all of my inefficient babbling thus far, all I've done is establish this integral. I'm really, really trying hard to get you to see like why and when we introduce integrals, because honestly, that's the hard part. You might have even noticed. You might be one of those people who's like, well, in a math class, I can like do integrals. I can even freaking do, like, I can do trigonometric substitutions. I can do U substitutions. I can even do integration by parts if you pay me enough money. But but that's when the teacher says, or the professor says, do this integral. If you actually said to me, if you gave me a word problem and said, now, do you have to set up an integral or not? And if so, set it up and do it. I'd be like, what? Like, that would be me in most math class. And if you're thinking like, I can do integrals, but if physics is going to ask me to start setting up integrals or knowing when to use integrals, well, this is what I'm here to say. Like, okay, we are setting up this work integral right now. We're setting up the integral of force with respect to displacement precisely because the force is varying continuously throughout the displacement. That's why we're setting up the integral, and we're giving it a name called work, like a physics name called work, and a unit called a joule. And if you're with me so far, you will note I have not solved the integral yet. Maybe that's also why you want to kill me right now. I have not solved the integral yet, and not one thing I've said about this integral implies how to solve it, nor do we even know for a fact that it is solvable at this point. I just want you to know an integral is a continuous sum. It's a thing that we want to be able to solve in physics and math. It's an idea. Like, what if we could add up all the blah, 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 and get the answer? Wouldn't that be productive? Yes, it would. Now, can we do that? Is there a way of doing that? Good questions. They're not answered yet. So we have not solved this integral. And there's nothing in what I'm saying that assumes, or there's no reason that anything I've said so far should have shown us how to solve the integral. This is about triple equal sign, what the integral is, not how to get its answer. That's number one. Number two, I still haven't said what we're going to do with that answer once we get it. Like, of course, that's my job, and I will. But just to try to like make these ideas clear. All I'm saying is so far that and if you're going to write anything down in addition to what I've written, what I'm saying so far is an integral is a continuous sum. An integral is not an antiderivative. I'm saying if you think an integral is an antiderivative, that's partly why sometimes you're confused. See, that's a double equal sign, not a triple equal sign. Okay. What I'm saying is the integral is. Oh my God. Oh my God. Okay, that's really weird. Yeah, I guess so. Okay. That's, and I get that, which also might be weird. Right. Okay. And you're totally listening clearly. So that's good. Whoa. Oh my God. Wait. Okay. Am I out of line now? Have I crossed? Oh my God. Have I crossed something? I fire myself. Does that help? You rebuke. Is that an expression? I rebuke. I might need more chat on that one. I've never even heard anybody say that. I'm like actually past the smelling salts. I'm actually quite horrified at myself that I just earned a I rebuke thee. And if you just made that up, like, wow. What I'm saying to everybody, okay. We're going to solve this integral. We are going to solve it. We're going to like apply it here. And the way, okay, wait, actually. Right. Well, yeah, okay, okay. Okay, I'm just going to read this. I'm going to go to the next page. I'm going to read this. Again, this is like mini. Again, I apologize. Well, I don't really apologize. This is a mini math lesson here, okay? Which, in my experience, we actually can benefit from at this moment. If nothing else, take this as the physicist perspective on the math required here. But so we've established the integral. It's like we've just invented the idea that we need an integral in our lives. And the example that we need the integral for in physics is the integral of force with respect to displacement. Obviously, there's like tons of other integrals. It could be like acceleration with respect to time or like anything. But so that's just saying we want the answer to this integral. Now, can we get an answer to this? Like, do we can we add up all the forces with respect to displacements when the displacements are infinitesimal? I don't freaking know. Like, just because we said we want the answer doesn't mean we know how to get it. Now, the reality is oftentimes we cannot. Let's just start with, just because someone writes down an integral doesn't mean it's solvable. The truth of the matter is most integrals are not solvable by analytical methods. Like, they can be approximated by computer programs or whatever, but most integrals that you just write down that you just want, whether you're a mathematician or a physicist, most of them are not solvable. And okay, so it's not just like an automatic thing. When they're solvable, there's different methods and techniques that we get used to for solving them, but that is a whole art form. And that's also why integrating in a calculus class is a harder chapter usually or a harder whole topic than differentiating. Okay, just to take the derivative. Once you learn how to take a derivative, any function that's continuous, once someone says take a derivative, it's doable, and there's usually a procedure to follow. Like, it's not, you just go down an algorithmic path and you take the derivative. With integration, first of all, you don't know at the outset necessarily if there is an answer. And second of all, if you do believe there's an answer, it's much more like puzzle solving or technique deployment integrating. It is more of an art than traditional science that way. Okay. But when we can, and I'm not saying the integrals in this class will be so particularly hard, but I'm trying to get underneath what an integral really is. When we can solve integrals, as we will be able to in this context, what we usually deploy in solving integrals, in computing the answer to these continuous sums, is the FTC, as I've written here at the bottom. Like it says, often we cannot, sometimes we can. When we can, we often deploy FTC. What is FTC? The fundamental theorem of calculus. Fundamental theorem of calculus, not the fundamental definition, not the fundamental axiom, the fundamental theorem. What am I talking about? I'm talking about, now it comes in many forms. There's actually many different versions of the fundamental theorem of calculus because it's like really fundamental. Here's the version I mean. Okay. Now, again, like this is Math Monday. I don't know what to, say, but was eye-opening to me when I first realized this, like after I'd been trying to do calculus for like 85 semesters. One way to say the fundamental theorem of calculus almost seems obvious when you write it this way. What I'm saying in English, what this theorem is saying is that given some function, some single valued function, some continuous function, y equals a function of x, then the definite integral, like from any one point A to any other point B, like the definite integral of the derivative of y with respect to x is simply the function y. Let me say that again. What we're saying here is given some well-behaved continuous function y equals f of x, the integral of the derivative, excuse me, let me say it. The integral from A to B of the derivative of y is y, evaluated from A to B. The integral of the derivative of a function is the function, evaluated in the same interval that integral was performed. Let me say it one more time. The integral over a certain region of the derivative of a function is the value of that function over that region. Now, there's a couple of reasons why this sort of sounds obvious, and maybe it sort of is, or at least there's a couple of reasons why this sounds hopefully like it makes sense. One reason is what it sounds like I'm saying. Well, no, one reason this makes sense is exactly why I wrote it here, because it looks like I'm just saying like the dx's cancel out. And that is what I'm saying in a way. I'm saying, yeah, it's actually not shocking that the integral of the derivative is the function. The integral of dy dx is the integral of dy, and the integral of dy just means add up all of the little intervals of y to get the whole y. The whole is equal to the sum of its parts. I'm writing it this way so that it does look like the sense that I'm trying to make, that the integral of the derivative of a function is in fact just the function. Another reason why this might make sense, or it might even sound vaguely familiar, is what I'm saying is that when you integrate a derivative, you just undo that derivative. I am saying here in this theorem that the integral is the inverse function of the derivative, that if you differentiate a function and then you integrate it, you just undo the derivative. You end up back where you started. In other words, what I'm saying here is what, of course, you've heard 1,000 times, and the thing that I was whispering before obnoxiously. What I'm saying here is, but I'm saying it, hopefully I'm sort of trying to, okay. What I'm saying here is, hopefully in a slightly different way, something that you've heard a million times. I'm saying but I want to make this clear. I'm saying the integral equals the antiderivative, double equal sign. Okay. When I'm pausing, when I'm taking the risk to spend time spelling out for you something, again, like I did not get, I misunderstood for a long time and it messed me up. And maybe I was alone, but I don't think I was. I'm saying that the integral triple equal sign the continuous sum. What an integral is a continuous sum. That's what it is. And that's why we need it. Whenever we need a continuous sum of products, we need an integral. Whether it's solvable or not is yet a different question. But if we're going to approach that question of how do we solve integrals, we think hard about what happens when we add up little slopes, when we add up a bunch of little slopes, and we realize, oh my God, the weird thing is that when we take a continuous sum, when we think about it, if we take a continuous sum of derivatives of functions, it turns out we're just freaking adding up the function. It turns out double equal sign, that the integral turns out To integrate a function is to anti-differentiate it. That's not what it means. That's what it turns out to be equivalent to. So it turns out, and this is so important, it's such a revelation, it's such a discovery, that we call it the fundamental theorem of calculus, because it enables us to actually compute integrals, because we realize, holy crap, this continuous something that we need for independent reasons turns out to be a derivative run in reverse, like this other branch of calculus. Like we thought we understood slopes of tangent lines. We thought we understood rates of change at points. And we did all this stuff with instantaneous acceleration, instantaneous velocity, points, free body diagrams at points of space and time. We have this whole world of physics and math built up around derivatives about infinitely small intervals and what kind of changes were occurring in those infinitely small intervals. Then that we reach a limit with all of that, we're like, oh yeah, that's great. But what if we ever want to like look at actually like a segment of time and space? What do we want to look at? A finite region, not a point, but we want to know what's happening to a force as it acts through an interval of time or space. So we like go to a different part of our brain and a different part of history and a different set of physicists and mathematicians. And we come up with this idea of like, oh, the continuous sum, the adding up an infinite number of small little intervals over a finite space and adding up products as we go. And we realize, okay, we need this new idea that involves infinity called an integral. It's a new idea of infinity because it's a finite chunk of space or time or whatever that's divided into an infinite number of infinitely small chunks. And we're like, but how are we going to, okay, that's great, that's what we need, but how are we going to like solve anything with that? How are we going to get these integrals? And we think about it, we're like, oh my God, wait, it turns out that the continuous sum, if we really think about it, well, it's a continuous sum of infinitely small intervals, actually is related to this other infinite thing called the derivative. It turns out that this new continuous something that we want is actually that old thing called the derivative run in reverse. We were trying to get away from derivatives and invent a whole new way of thinking, but it turns out the whole new way of thinking is doable if we remember our derivatives. That is a breakthrough. That's a fundamental theorem. What we're saying is, oh, frick, the integral means the continuous sum, but what the integral is, double equal sign, is the antiderivative. So in order to compute integrals, we can often do derivatives backwards, and that's what we do. I'm about to move on, but what I'm really saying is, I know you've heard a million times that the integral is the antiderivative. And I even know you've heard the fundamental theorem of calculus a million times. If you're anything like me, you thought two things while all that was happening, but you didn't realize you were thinking them. If you're like me, one, I basically kept thinking is the fundamental theorem of calculus sounds totally stupid. The fundamental theorem of calculus is the integral of a derivative is the original function. Like the integral is the antiderivative. How is that a fundamental theorem? Like that is a freaking integral. Like didn't we know that from the start? I'm here to say, no, we didn't. What we knew from the start is that the integral is a continuous sum. And now we're discovering that the way to solve that is by running a derivative backwards. That's the importance of this. And and why is it true? Because of what I just wrote here. So now we're going to say, and I know we're running out of 12 minutes. So I'm still on point number one, like solving this integral. So here, sorry. Right. So now I'm finally going to plug in. I know it's 9 minutes. I'm now going to like apply back to the physics. Again, what I'm trying to do now is compute the integral. That's like step one of this part. What I'm going to do with that computation is then step two. I haven't said that yet, but I'm just going to go step by step. So we want to compute the continuous sum of force throughout displacement in the case here where the force is negative kx, like, which is what began this whole discussion. Like the force is changing at every single x, changing in as simple a way possible linearly, but the force is a continuous function of x. That function is f equals negative kx. So we want right? Like I'm just plugging in negative kx for f here. Oh, I'm going to tell you later this semester why I'm sort of being fussy and holding on to these vector symbols as I go, because eventually we'll care. So technically, technically integral is technically work is the integral of the product of force times displacement. And technically force is a vector and displacement is a vector. And it actually ultimately becomes important to keep track of that fact that they both have direction. And this is technically the dot product or the scalar product of those two directional quantities. So that's why I've been keeping track of the arrows. However, here, we're going to get more into the details of that later. But again, in general, we have to care about the fact that force has direction and displacement has direction. And they might or might not match up nicely in a particular example. But here they totally do. The displacement is along the x-axis. The force is directly along the x-axis and pointing the same direction. So I'm getting rid of the vector symbols. I'm saying we don't have to do anything fancy. And then I'm saying we got a negative sign here, and we've got these. I want to get rid of the negative sign so I can go like this. Because when you evaluate a definite integral, you're doing the top answer minus the bottom answer. So if you, okay, well, we can talk more about that. If you have questions about that, let me know. But I just got rid of the negative sign by flipping the limits of integration. Now K is, we're just about out of time. So let me just do this. Here's where I've got an integral. I've got to solve it now. In principle, I have no idea how to solve it. But if I use FTC, if I know that the integral is if I know that to solve integrals I do derivative backwards. What I'm asking for is we want the function such that its derivative with respect to x is kx, right? We want y equals f of x such that dy dx equals kx. Well, you know how to take derivatives, especially with algebraic functions. You know the power rule. So we're just running the power rule in reverse here. Like, you know that the derivative, you know that, and I'm saying this quickly because we have 4 minutes left, but you know that the derivative of ax to the n, I guess I'll write this down, is anx to the n minus 1, right? So we're just literally going to do this in reverse here. And I'm relying on you to know that. So I'm saying that the integral here if we want the function, if we want the derivative to be kx, then the original function we've got going on, as I'm sure you've guessed, is kx squared over 2, right? Evaluated. And that's the part that most of you are familiar with from knowing that, from thinking that derivatives are antiderivatives. I'm just trying to break this down for you in my physics fashion. So I'm saying this is the work done by the spring to displace the mass from x naught to 0. Now we've got 2 minutes left. That does not answer the question here. It does not answer the question. The question is, what do we do with work? We're gonna have to continue this next time. And this is the part I'm gonna do probably in the other class and maybe watch the other video to get it more specifically. I'm just looking at the clock to see if I can do this now. Well, I'm gonna stop talking. We've got 2 minutes. I'm gonna stop talking. I'm just gonna write something. I'm gonna ask you to copy it. It may make instant sense to you. It may clarify, it might finish this whole thing for you, or it might tell you what exactly for us to start off with next class and for you to ask me questions about. But do you think I'm just going to end on today? I see it's 1:30. The point of this whole big discussion we just had, and again, I apologize to some of you, and I say you're welcome to some of you. This was all a big romp and frolic about what the work integral means for good or for bad. It's about what it means and how to compute it. What's the point of the work integral? The point is that for each little bit of work we do, F net equals ma. For every little bit of force through displacement, we're doing an ma through displacement. For every little bit of work where the a is constant, a always equals v squared minus v naught squared over 2x, you might recall from kinematics, for every little bit. So for every little bit of work we do, every little bit of work we do, we change the amount of 1/2 mv squared in a system. That's what I just proved algebraically in 2 lines here. The point of work is that it takes the product of half the mass and the square of the speed of a system, something I would not otherwise care about at all. I would never care about the square of the speed of something times half its mass. But evidently, if I track that quantity, if I look at a system and say, hey, what's the square? What's your speed? Oh, square. Oh, what's your mass? Oh, divide by 2, multiply the 2 together. If I just put that number in a box and I do work on that system, that number in the box will change by precisely the amount of joules of work I do. Work measured in joules on a system is change in 1/2 mv squared measured in joules of that system. So from here on in, we give that 1/2 mv squared thing a name. We call it energy. And from here on in, we say that work transfers energy. I'll back up and explore that more next time. But the point of this whole thing of getting the work is that it tells you how much energy 1/2 mv squared is changed in a system. I'll leave it at that. We're just going to keep going Wednesday. Sorry to keep you over time. Hopefully that clarified some things. We're still not done with question 4. I still haven't gotten it, although now you could solve. Now you have enough to solve, but we will pick up with this on Wednesday and we'll get the answer to question 4, which is 3.78 meters per second, I think, or maybe 3.87 meters per second. But thank you, you've been very patient. I'll hang out for any questions if there are, but thank you very much. Totally. Thank you. Have a great day. Have a great day. I'm stopping the recording. I'll see you tomorrow too. Thank you guys. And I'm staying here in case there's any questions. Thank you. Thank you. Stop it.